Okay. The concept of couples here is really cool because you can work a lot of problems out in your head. The previous problem, it looked kind of complicated, but understanding couples, I could just do it in my head. And I did it in my head for you on the previous video. This one you can do pretty much in your head too. 600 cosine 30 in one direction, 600 cosine 30 in the other direction. So it's 600 cosine 30 times zero point 0.2 in the counterclockwise, 600 sine 30 times the same 0.2, the radius, the distance is 0.2 both times. So you just add this up. Takes a calculator. I mean, sine 30 is easy, but cosine 30 isn't. I mean, you have to grab a calculator for that. So it'll give us a moment of 43.9 Newton meters in the clockwise direction, tending in the clockwise. Now you could do it this way. I don't know if I really want to mess with that. Let's see. How would you think about, how would you calculate D and the perpendicular distance? It's messy. In other words, this makes it easy. Okay, let's go on. Equivalent systems. Now, you have several forces acting on a system, and we want to make them into a force and a moment. Force is a sliding vector. You can slide it to any point on its line of action. A couple moments of free vector. It's the same anywhere, as we demonstrated. So for point O not on a force's line of action, a force acting at point A can be replaced by a force acting at point O and a couple. So here you have a moment, applied moments, and you have force in a moment about point O due to two forces. So you can add force 1 and force 2 to get the force acting at point O, and then you can add up the three moments. You have the moments generated by the forces, and then another moment externally applied, a shaft, a crankshaft, an axle, something like that. You have some sort of moment applied, and then you have forces, and then you have a system of forces. So now you can replace it with one force and one moment acting at O. Okay, these little figures demonstrate forces and moments. We can make this equivalent. You'll notice equivalency here. This force acting here is equivalent to these two forces, one up, one down, okay? And then this force, and these two cancel, leaving this force, but then you also have to replace it with the moment that's generated about this point. And of course, here's the idea here. If you push it, force acting at the end of the rod's the same as a force acting at the other end. Pulling. Okay. Now, we want an equivalent force system here, separating these two out. You'll notice this is 3, 4, 5, right triangle. This is the sines and cosines of 30. So this is a 1.5 kilonewtons acting up. And this is 0.866 times 3, which 2.6 something acting to the right. When you have a similar triangle, this is kind of neat. 5 kilonewtons magnitude means you have 3 kilonewtons in the x-axis direction and 4 kilonewtons in the y-axis direction. Negative y, excuse me, negative y. And when you run the numbers, you'll get 4 and 3. So now we have forces aligned along our coordinate axis. We can just add up all the moments about point O. So it's 3 times 0.1, 3 cosine 30 times 0.1. This is the positive one. This would, oh, excuse me, this would be a negative one. This would be a positive moment. This would be a negative moment, 4 times 0.2. 4 times 0.5, also negative, and 3 times, or 1.5, 3 times sine 30 times 0.2. Crunch the numbers, all the positives and negatives, and this could be done on a calculator. Obviously, we don't have all those vector cross products we have to worry about. A lot of the stuff I did on Excel, we could have done on a calculator. But getting it all set up in Excel makes the three-dimensional problems a lot easier. You just plug in the numbers and crunch it. Okay, so we're going to get total force, and we'll get x and y coordinates of the force, total force, positive x, negative y, and we can get the force in direction. Okay. Now, the moments. So you've got the got to add up all the moments times their lever arms. Now we've divided the forces up into their components. That's what we've done. And of course, this is a calculator problem, as you can tell. This force, 5.598 kilonewtons to the right, 6.5 kilonewtons down, and 2.46 kilonewtons clockwise, will produce the same reactions at the wall as those produced by the original system. That's the point of equivalent systems. We want to get to something that's, instead of figuring out this original system, oh, how do we handle it? How do we know the reactions at the wall? Stuff like that. Instead of trying to figure out each one individually and all that, we can use this equivalent force system to get that. Okay. So a single force acting at so here's an idea. Well, here's if the force and moment, if you reduce to a force and moment which are perpendicular to each other, and you'll notice on this problem it is, the moment's coming in and out of the page. It's in the negative z direction, and the force is perpendicular to that. So you can get an equivalent force. You can move that force to a point away from point O, probably up here somewhere, that would create the same moment. This same force acting at a different point would cause the same moment. In fact, you could probably go over here. That'd probably be the best place, is right there, to cause the same moment. And you'll notice that in this little diagram. Here's the moment going this way, the force is perpendicular. You move a certain distance, That distance is given by the moment divided by the magnitude of the force, perpendicular to both. So these are some reduction rules, if you will. Write these rules down on a card so you have them handy. Concurrent forces, just add them up. So a single force acting at point O, boom. No moments about point O. You're done. Easy. So now we have, this. Let's see. So now here we can calculate this as a single force about point O, or a single force acting at D from point O. Of course, point O is an arbitrary choice. You can choose it wherever you want. Parallel forces. You're going to have a resultant force, which is going to be along the z-axis in this case, point O. Or it's going to be parallel to the z-axis. It might be off the z-axis. And here's the moment is going to be in the xy plane. All the forces are parallel to the z-axis. The moment's in the xy plane somewhere. So you can also find the distance d, where you can put the F in such a way that it creates the same, that's equivalent to this force system. Okay. Now, we had a special case where the force and moment were perpendicular. Next, we're going to consider when they're not. And we're going to look at reducing this system. In the next video,